I would like to go over the instructions for exam number 3. Exam number 3 will be Friday, April the 24th. The exam will begin at 12 noon. That's the regular classroom time. So the exam will begin at 12 noon on Blackboard. It will appear as a test on Blackboard. There is a 120-minute time limit on the exam. Normally, I would think this exam would be done in 50 minutes, but to account for the inevitable delays with Blackboard, I've set the time limit to 120 minutes. The exam must be completed in one setting. So you cannot stop and restart the exam. So arrange your schedule so that at noon on Friday you can sit down and devote 2 hours to this exam, and it needs to be completed in one setting when you start the exam. And furthermore, after you've responded to a question, it cannot be revisited. So you make sure your response is what you want to enter. Click the button and you'll move on to the next question, and you can't go back. Your answer is locked in and you can't go back and change it. Regarding the questions, some of the questions will be multiple choice. I expect you'll be able to work through those pretty easily. Or at least you can be able to click the button pretty easily. Some of the questions will require you to enter a numerical answer. I'm going to try to write the instructions in such a way that so you will know what form the number needs to take. And you need to pay some attention to that because your answer will be compared to the numerical answer that I enter as the answer, and hopefully we'll get it to be where Blackboard will grade this. But in order to do that, you have to put in the number in the right form. So if it asks for megahertz, then the number needs to be in megahertz, and if it asks for a certain number of decimal points, you need to have a certain number of decimal points. Otherwise, the number won't match. Some questions will require you to enter a formula into the response window, and the Blackboard program has an equation editor, so you will be able to get all the mathematical symbols into the equation. So some questions will have that requirement. Now, to give you a little practice, I'm putting up a little quiz with this announcement, and the purpose of this is just to get you to practice entering responses into the exam window. So I encourage you to do that, just so you'll know what the windows look like and how to work this equation editor for the questions that require you to enter an equation. So for the topics on the exam, I would like to pick up the topics with angle modulation, that's frequency modulation, and phase modulation. We've looked more at frequency modulation. So the topics we discussed: instantaneous frequency and frequency deviation, block diagrams for modulation and demodulation, the time domain equations and signals for a series approximation using Bessel functions, the spectra equations and graphs, Carson's rule for the bandwidth, the power in the FM signal, and we looked a bit at the Armstrong wideband FM system, which uses frequency multiplication, and then mixers and local oscillators, And bandpass filters to start so that a narrowband FM signal can be ramped up to a wideband FM signal and shifted to the appropriate frequency for transmission. So with FM, we looked at frequency mixing. This is using a mixer and a local oscillator and a bandpass filter to shift the frequency of an FM modulated signal from one center frequency to another. Frequency multiplication, which increases both the center frequency and multiplies the frequency deviation. Then that's the end of the FM material, it looks like. Then next topic, we talked a bit about autocorrelation. The autocorrelation function where you can find the total power and the DC power in a random signal. And then we mentioned power spectral density. The total power is the integral overall frequency of the power spectral density. And the power in a given frequency range, you integrate over that frequency range. We have the topic of signal sampling, ideal sampling with delta functions, natural sampling with rectangles, and then flat top sampling with a sample and hold type system. So we discussed those forms of sampling. We spent some time with the Nyquist sampling theorem, which establishes the minimum sampling rate required for successful reconstruction of the message signal from the samples. And we discussed aliasing and the anti-aliasing filter. Next topic was signal quantization, where we turn the sampled signal into its nearest standard value. This is the analog to digital conversion process. Have a certain number of levels for the quantization. The levels are given by the number of bits. Number of levels equals 2 to the power of the number of bits. That should be an N. And in the process of quantization, you introduce quantization noise. So we have an equation to determine the signal to noise ratio for uniform quantization with a certain number of levels. And we also have an equation to determine the signal to noise ratio for a non-uniform system using a mu law compressor. And at the end of this process, we can determine the digital bit rate. We're taking an analog signal, turning it into a string of binary numbers, and that produces a binary signal that proceeds at a certain bit rate. And the bit rate is equal to the sampling rate in samples per second. Then you multiply that by the number of bits per sample. That's an N again. So samples per second times bits per sample gives you bits per second as the bit rate. We then discussed turning this string of ones and zeros into a binary signal, and you have to determine what kind of encoding you wish to use. We looked at different forms of encoding with these names like unipolar, non-return to zero, and polar, non-return to zero, and then some return to zero type signals. And you have examples of those in the notes, and it matters which one you choose for that because they have different spectrums, different frequency characteristics. Some have DC components, some don't have DC components. Some have wider bandwidth than others, and I'll refer you to your notes to determine the characteristics of each one of these digital encoding formats. When the binary signal is encoded in whichever one of the choices we have, then that signal is used to modulate a carrier. And we looked at 3 different ways of modulating the carrier. There is on-off keying, which is essentially an amplitude modulation, frequency shift keying, which is a frequency modulation, and phase shift keying, which is obviously a phase modulation. We looked at the characteristics of each of those. Then we looked at the phase shift keyed signal in terms of its constellation diagram, which is essentially a phasor diagram for each of the possible digital or modulated signals. So it's a phasor diagram of the modulated signals where we're just using the dots at the end of the phasor as points in the constellation. And then looked a bit at quadrature amplitude modulation, where the binary signal is broken into words, symbols of a certain number of bits, 2, 4, 8, whatever the, 2 or 4, 2, 3 or 4. We're not going to look at any more symbols than that. It's conceivable that you could have, but so we looked at block diagrams that would produce a quadrature amplitude modulated signal and the corresponding constellation diagrams, and then discussed how we can use synchronous demodulation to retrieve from the quadrature AM signal. We can retrieve from the symbol values using a synchronous demodulation system. Circumstances prevented me from returning your last exam to you, so I would like to go over my solution for exam number 2. So you'll see what I was looking for that exam. Now, the first question, this is a form of double sideband amplitude modulation. We've got two cosines. The first cosine 2 pi 1000t, frequency 1000, has a phase shift of minus 30 degrees. The second cosine has a frequency of 10,000, and we're applying a phase shift of minus 90 degrees. And the first question is, what is this time signal that is the result? And we simply perform the multiplication. We have cosine 2 pi 1000t minus 30 degrees times cosine 2 pi 10,000t minus 90 degrees. You can then apply the trig identity if you wish, and we would have 1/2 the sum of the angles, 1/2 times the cosine of the sum of the angles. Well, I'm sorry, that looks like the difference of the angles. This is 1/2 cosine of the difference of the angles plus 1/2 the cosine of the sum of the angles. Okay. The next part of the question asks for the Fourier transform of this time function. So let's see, the way I took this first time equation, cosine 2 pi 1000t minus 30 degrees times cosine 2 pi 10,000t minus 90 degrees, and then did the Fourier transform for each and then convolved them together. So the first cosine gives a 1/2 using our Fourier transform for the cosine of an angle with, or the Fourier transform of a cosine with a phase shift. That gives us 1/2 e to the minus j30 delta f minus 1000 plus 1/2 e to the plus j30 delta f plus 1000. That's convolved with the Fourier transform of the second cosine. 1/2 e to the minus j90 delta f minus 10,000 plus 1/2 e to the plus j90 delta f plus 10,000. When you convolve these across each other, we get 1, 2, 3, 4 terms. 1/2 times 1/2 gives 1/4. E to the minus j90 times e to the minus j30 gives e to the minus j120, and then we have f minus 10,000 minus 1,000, so that's f minus 11,000. Second convolution, 1/2 times 1/2 is 1/4. E to the minus j90 times e to the plus j30 is e to the minus j60. Then f minus 10,000 plus 1,000 gives delta f minus 9,000. Then for the third one, 1/2 times 1/2 is 1/4. E to the plus j90 times e to the minus j30 is e to the plus j60 plus 10,000. minus 1,000, that's F, delta F plus 9,000. I was looking at the wrong equation. Then 1/2 times 1/2 is 1/4. E to the plus j 90 times e to the plus j 30 is e to the plus j 120. Then F plus 10,000 plus 1,000 is delta F plus 11,000. So this is the, there's 4 delta functions in the Fourier transform. Next question asks us to plot those. So we have the 4 delta functions at the appropriate frequencies. They all have a scale of 1/4. And I plotted out the angles for each one as well. And this is the result that I got. Okay, problem number 2, write the equation as shown in this graph. So what I see is an amplitude modulated signal. The envelope is, see, we've got a constant value of 2 here, and then on top of that is this triangle shape. So if I can write an equation for a constant and a triangle in the middle and then a constant, and then that would be the envelope for this amplitude modulated signal. That's the kind of equation I want to write. And then we're going to find the Fourier transform and sketch the Fourier transform. So the format this is, for this amplitude modulated signal, for the amplitude 2 plus 4 triangle t over 2 will give the constant multiplying or with the triangle setting added to that, and then that forms the envelope multiplying this cosine, which happens to have a frequency of 5. So to sketch that out, you would see if this is the 0 line, then you would draw the mirror image, and then the sinusoid would fit inside that envelope. So that's the form of the equation. Let's see, then I factored out a 2 from the first part, and now I want to find the Fourier transform of this equation. And so 2 is an amplitude multiplier. I have 1 plus 2 triangle t over 2. Fourier transform, 1 transforms, Fourier transform 1 is delta f. And then the triangle, let's see, apply the time scaling theorem, we get a 4 sinc squared of 2f. And then this multiplication becomes convolution, and we're convolving with the Fourier transform of the cosine, 1/2 delta f minus 5 plus 1/2 delta f plus 5. The 2's cancel the 1/2s. And then you carry out the convolution. Delta f minus 5 convolved with this delta f gives a delta f minus 5. Delta f minus 5 convolved with this sinc squared gives a 4 sinc squared f minus 5 divided by 1/2. Then the second one, delta f plus 5 convolved with delta f gives a delta f plus 5. Then a delta f plus 5 convolved with this other sinc squared gives a 4 sinc squared f plus 5 over 1/2. So we've got delta functions. I changed my mind a couple of times when I did the sketch, but we've got these delta functions. Let me highlight those in yellow. Here's delta functions. 2 delta functions at the frequency of 5 hertz, and then we've got on top of that this sinc squared shape centered at 5 hertz. You're shifted to be centered at 5 hertz, and then the 0, it touches 0 at 1/2 unit above and below that. So that's my sketch for the Fourier transform. Number 3, we're taking a message signal with a bandwidth of 10 kilohertz, and that's used to create this modulated signal. So here's the message signal with a bandwidth of 10 kilohertz multiplying a carrier at frequency f0, which happens to be 455 kilohertz. And so this is a double sideband FM signal that is being shifted to a different frequency by using this mixer in the bandpass filter. So we're mixing with a local oscillator of a certain frequency, passing it through a bandpass filter, and we want to produce a signal at 650 kilohertz. So, 455 plus and minus the frequency of the local oscillator is going to give us two values, one of which we need to be 650. So frequency of a local oscillator plus and minus 455 is equal to 650. So we get a couple of choices, 1105 or 195. I had to change my mind one time there. So that gives us the local oscillator. The center frequency, well, we're looking for 650 kilohertz signals, so we're going to filter out select the component centered at 650 kilohertz. And for double sideband, the bandwidth of the modulated signal is twice the bandwidth of the message signal. So that's 20 kilohertz. Number 4, we've got this modulated signal, which is given by this equation into a full wave rectifier, and then I want to see what the signal is coming out of the rectifier. So we have an equation, and we're asked to sketch this. Now it's been jumbled a bit, but you can easily see that you can rearrange this in a form that we've been more familiar with as a amplitude modulated signal. So the envelope for the signal is this term in brackets, which is a value of 2, and then we're adding a rectangle with a height of 2 right in the middle, and the rectangle has a width of 4. So that gives us this part of the envelope, and when we sketch the signal, we then mirror image that, so we'll get the envelope that looks like that, and then the cosine with a frequency of 2 fits inside that envelope. So this is the sketch I'm looking for. This is rectified. I'm presuming I think a full wave rectifier, or at least that's what I'm going to sketch. And when it's rectified, all of the negative values are turned into positive values, and the sketch will look something like this. Now, I'm a bit particular about these sketches for rectified signals. There are sometimes people will draw something that looks like this. This is not a rectified signal. I'm looking specifically for these straight lines as they intersect the 0 line. No, that is not a sketch for a rectified signal. We've got to have the straight lines as it intersects the 0 line. And I'm working on the presumption that if you're not careful enough to draw an accurate picture, I can't be sure that you understand what the rectifier is doing.